Europium. Europium is a chemical element with symbol EU and atomic number 63. It was isolated in 1901 and is named after the continent of Europe. It is a moderately hard, silvery metal which readily oxidizes in air and water. Being a typical member of the lanthanide series, europium usually assumes the oxidation state +3, but the oxidation state +2 is also common. All europium compounds with oxidation state +2 are slightly reducing. Europium has no significant biological role and is relatively non-toxic compared to other heavy metals. Most applications of europium exploit the phosphorescence of europium compounds. Europium is one of the least abundant elements in the universe. Only about 6992500000000000000 black spade 5 times 10⁸% of all matter in the universe is europium. Europium is a ductile metal with a hardness similar to that of lead. It crystallizes in a body-centered cubic lattice. Some properties of europium are strongly influenced by its half-filled electron shell. Europium has the second lowest melting point and the lowest density of all lanthanides. Europium becomes a superconductor when it is cooled below 1.8 K and compressed to above 80 GPa. This is because europium is divalent in the metallic state, and is converted into the trivalent state by the applied pressure. In the divalent state, the strong local magnetic moment suppresses the superconductivity, which is induced by eliminating this local moment. Europium is the most reactive rare earth element. It rapidly oxidizes in air, so that bulk oxidation of a centimeter-sized sample occurs within several days. Its reactivity with water is comparable to that of calcium, and the reaction is. Because of the high reactivity, samples of solid europium rarely have the shiny appearance of the fresh metal, even when coated with a protective layer of mineral oil. Europium ignites in air at 150 to 180 degrees C to form europium oxide. Europium dissolves readily in dilute sulfuric acid to form pale pink solutions of the hydrated EU, which exist as a nonahydrate. Although usually trivalent, europium readily forms divalent compounds. This behavior is unusual to most lanthanides, which almost exclusively form compounds with an oxidation state of +3. The +2 state has an electron configuration 4f7 because the half-filled F shell gives more stability. In terms of size and coordination number, europium and barium are similar. For example, the sulfates of both barium and europium are also highly insoluble in water. Divalent europium is a mild reducing agent, oxidizing in air to form EU compounds. In anaerobic, and particularly geothermal conditions, the divalent form is sufficiently stable that it tends to be incorporated into minerals of calcium and the other alkaline earths. This ion exchange process is the basis of the negative Europium anomaly, the low europium content in many lanthanide minerals such as monazite, relative to the chondritic abundance. Bastnasite tends to show less of a negative Europium anomaly than does monazite, and hence is the major source of europium today. The development of easy methods to separate divalent europium from the other lanthanides made europium accessible even when present in low concentration, as it usually is. Naturally occurring europium is composed of two isotopes, 151Eu and 153Eu, with 153Eu being the most abundant. While 153Eu is stable, 151Eu was recently found to be unstable to alpha decay with half-life of 70261577880000000000 black spade 5 + 11 3 times 1018 years, giving about 1 alpha decay per 2 minutes in every kilogram of natural europium. This value is in reasonable agreement with theoretical predictions. Besides the natural radioisotope 151Eu, 35 artificial radioisotopes have been characterized, the most stable being 150Eu with a half-life of 36.9 years, 152Eu with a half-life of 13.516 years, and 154Eu with a half-life of 8.593 years. All the remaining radioactive isotopes have half-lives shorter than 4.7612 years, and the majority of these have half-lives shorter than 12.2 seconds. This element also has 8 metastates, with the most stable being 150MeU, 152M1EU and 152M2EU. The primary decay mode for isotopes lighter than 153U is electron capture, and the primary mode for heavier isotopes is beta- decay. The primary decay products before 153U are isotopes of samarium and the primary products after are isotopes of gadolinium. Europium is produced by nuclear fission, but the fission product yields of europium isotopes are low near the top of the mass range for fission products. Like other lanthanides, many isotopes, especially isotopes with odd mass numbers and neutron-poor isotopes like 152U, have high cross-sections for neutron capture, often high enough to be neutron poisons. 151EU is the beta decay product of samarium 151, but since this has a long decay half-life and short mean time to neutron absorption, most 151SM instead ends up as 152SM. 152EU and 154EU cannot be beta decay products because 152SM and 154SM are non-radioactive, but 154EU is the only long-lived shielded nuclide, other than 134CS, to have a fission yield of more than 2.5 parts per million fissions. A larger amount of 154EU is produced by neutron activation of a significant portion of the non-radioactive 153EU, however, much of this is further converted to 155EU. 155EU has a fission yield of 330 parts per million for uranium-235 and thermal neutrons. Most of it is transmuted to non-radioactive and non-absorptive gadolinium-156 by the end of fuel burnup. Overall, europium is overshadowed by cesium-137 and strontium-90 as a radiation hazard, and by samarium and others as a neutron poison. Europium is not found in nature as a free element. Many minerals contain europium, with the most important sources being bastnasite, monazite, xenotime, and loperite. No europium-dominant minerals are known yet, despite of a single find of a tiny possible EUO or EUOC system phase in the Moon's regolith. Depletion or enrichment of europium in minerals relative to other rare earth elements is known as the Europium Anomaly. Europium is commonly included in trace element studies in geochemistry and petrology to understand the processes that form igneous rocks. The nature of the Europium anomaly found helps reconstruct the relationships within a suite of igneous rocks. Divalent europium in small amounts is the activator of the bright blue fluorescence of some samples of the mineral fluorite. The reduction from EU3+ to EU2+ is induced by irradiation with energetic particles. The most outstanding examples of this originated around Weardale and adjacent parts of northern England. It was the fluorite found here that fluorescence was named after in 1852, although it was not until much later that europium was determined to be the cause. Europium is associated with the other rare earth elements and is, therefore, mined together with them. Separation of the rare earth elements is a step in the later processing. Rare earth elements are found in the minerals bastnasite, loperite, xenotime, and monazite in mineable quantities. Bastnasite is a group of related fluorocarbonates, LO, and monazite is a group of related of orthophosphate minerals LNPO4, loperite is an oxide, and xenotime is an orthophosphate PO4. Monazite also contains thorium and yttrium, which complicates handling because thorium and its decay products are radioactive. For the extraction from the ore and the isolation of individual lanthanides, several methods have been developed. The choice of method is based on the concentration and composition of the ore and on the distribution of the individual lanthanides in the resulting concentrate. Roasting the ore and subsequent acidic and basic leaching is used mostly to produce a concentrate of lanthanides. If cerium is the dominant lanthanide, then it is converted from cerium to cerium and then precipitated. Further separation by solvent extractions or ion exchange chromatography yields a fraction which is enriched in europium. This fraction is reduced with zinc/amalgam, electrolysis, or other methods converting the europium to europium. Europium reacts in a way similar to that of alkaline earth metals and therefore it can be precipitated as carbonate or as CO precipitated with barium sulfate. Europium metal is available through the electrolysis of a mixture of molten EuCl3 and NaCl in a graphite cell, which serves as cathode, using graphite as anode. The other product is chlorine gas. A few large deposits produce or produced a significant amount of the world production. The Bian-Obio iron ore deposit contains significant amounts of bastnasite and monazite and is, with an estimated 36 million tons of rare earth element oxides, the largest known deposit. The mining operations at the Bian-Obio deposit made China the largest supplier of rare earth elements in the 1990s. Only 0.2% of the rare earth element content is europium. The second large source for rare earth elements between 1965 and its closure in the late 1990s was the Mountain Pass rare earth mine. The bastnasite mine there is especially rich in the light rare earth elements and contains only 0.1% of europium. Another large source for rare earth elements is the loparite found on the Kola Peninsula. It contains besides niobium, tantalum, and titanium up to 30% rare earth elements and is the largest source for these elements in Russia. Europium compounds tend to exist trivalent oxidation state under most conditions. Commonly these compounds feature EU bound by 6,9 oxygenic ligands, typically water. These compounds, the chlorides, sulfates, nitrates, are soluble in water or polar organic solvent. Lipophilic europium complexes often feature acetylacetonate-like ligands, e.g., UFOD. Europium metal reacts with all the halogens. This route gives white europium fluoride, yellow europium chloride, gray europium bromide, and colorless europium iodide. Europium also forms the corresponding dihalides, yellow-green europium fluoride, colorless europium chloride, colorless europium bromide, and green europium iodide. Europium forms stable compounds with all of the chalcogons, but the heavier chalcogons stabilize the lower oxidation state. 3 oxides are known: Europium Oxide, and the mixed valence oxide EU304, consisting of both EU and EU. Otherwise, the main chalcogenides are europium sulfide, europium selenide, and europium telluride. All 3 of these are black solids. EUS is prepared by sulfiding the oxide at temperatures sufficiently high to decompose the EU203. The main nitride is Europium Nitride. Although europium is present in most of the minerals containing the other rare elements, due to the difficulties in separating the elements, it was not until the late 1800s that the element was isolated. William Crookes observed the phosphorescent spectra of the rare elements, including those eventually assigned to europium. Europium was first found in 1892 by Paul-Émile Lecoq de Bois-Baudran, who obtained basic fractions from samarium gadolinium concentrates which had spectral lines not accounted for by samarium or gadolinium. However, the discovery of europium is generally credited to French chemist Eugène Anatole Desmarquet, who suspected samples of the recently discovered element samarium were contaminated with an unknown element in 1896 and who was able to isolate it in 1901. He then named it europium. When the europium-doped yttrium orthovanadate red phosphor was discovered in the early 1960s, and understood to be about to cause a revolution in the color television industry, there was a scramble for the limited supply of europium on hand among the monazite processors, as the typical europium content in monazite is about 0.05%. However, the Molycorp bastnasite deposit at the Mountain Pass rare earth mine, California, whose lanthanides had an unusually high europium content of 0.1%, was about to come online and provide sufficient europium to sustain the industry. Prior to europium, the color TV red phosphor was very weak, and the other phosphor colors had to be muted, to maintain color balance. With the brilliant red europium phosphor, it was no longer necessary to mute the other colors, and a much brighter color TV picture was the result. Europium has continued to be in use in the TV industry ever since, as well as in computer monitors. Californian bastnasite now faces stiff competition from Bian-Obio, China, with an even richer europium content of 0.2%. Frank Spedding, celebrated for his development of the ion exchange technology that revolutionized the rare earth industry in the mid-1950s, once related the story of how he was lecturing on the rare earths in the 1930s, when an elderly gentleman approached him with an offer of a gift of several pounds of Europium oxide. This was an unheard of quantity at the time, and Spedding did not take the man seriously. However, a package duly arrived in the mail, containing several pounds of genuine europium oxide. The elderly gentleman had turned out to be Herbert Newby McCoy, who had developed a famous method of europium purification involving redox chemistry. Relative to most other elements, commercial applications for europium are few and rather specialized. Almost invariably, its phosphorescence is exploited, either in the +2 or +3 oxidation state. It is a dopant in some types of glass in lasers and other optoelectronic devices. Europium oxide is widely used as a red phosphor in television sets and fluorescent lamps, and as an activator for yttrium-based phosphors. Color TV screens contain between 0.5 and 1 g of europium oxide. Whereas trivalent europium gives red phosphors, the luminescence of divalent europium depends strongly on the composition of the host structure. UV to deep red luminescence can be achieved. The two classes of europium-based phosphor, combined with the yellow/green terbium phosphors, give white light, the color temperature of which can be varied by altering the proportion or specific composition of the individual phosphors. This phosphor system is typically encountered in helical fluorescent light bulbs. Combining the same three classes is one way to make trichromatic systems in TV and computer screens. Europium is also used in the manufacture of fluorescent glass. One of the more common persistent afterglow phosphors besides copper-doped zinc sulfide is europium-doped strontium aluminate. Europium fluorescence is used to interrogate biomolecular interactions in drug discovery screens. It is also used in the anti-counterfeiting phosphors in euro banknotes. An application that has almost fallen out of use with the introduction of affordable superconducting magnets is the use of europium complexes, such as EU3, as shift reagents in NMR spectroscopy. Chiral shift reagents, such as EU3, are still used to determine enantiomeric purity. A recent application of europium is in quantum memory chips, which can reliably store information for days at a time. These could allow sensitive quantum data to be stored to a hard disk-like device and shipped around the country. There are no clear indications that europium is particularly toxic compared to other heavy metals. Europium chloride, nitrate, and oxide have been tested for toxicity. Europium chloride shows an acute intraperitoneal LD50 toxicity of 550 mg/kg and the acute oral LD50 toxicity is 5000 mg/kg. Europium nitrate shows a slightly higher intraperitoneal LD50 toxicity of 320 mg/kg, while the oral toxicity is above 5000 mg/kg. The metal dust presents a fire and explosion hazard,